Picture this. You're running a water treatment plant and suddenly your pumps stop responding. Your screens go dark. Your phone starts ringing with calls about water pressure drops across the city. This isn't a mechanical failure, it's a cyber attack. And unfortunately, this scenario is playing out more and more in industrial facilities around the world. I'm Alana, and in my 35 years working with industrial control systems, I've seen the landscape change dramatically. Today, we're diving deep into IEC 62443, the cybersecurity standard that could have prevented many of these incidents. We're going to cover a lot of ground today. We'll start with what 62443 actually is, break down the standard structure with real examples, look at the major 2024 updates, explore practical implications for your facility, and finish with concrete next steps you can implement immediately. This isn't going to be a theoretical discussion. Everything we cover today comes from real-world implementation experience. Let me be clear about something. ISA IEC 62443 isn't just another standard gathering dust on a shelf. This is what I call the building code for industrial cybersecurity. Look at these key characteristics. It's globally recognized, it bridges the gap between IT and OT security, and most importantly, it was developed by practitioners who understand industrial realities. Here's what makes this different from typical IT security approaches. When industrial systems get compromised, we're not just talking about stolen data or website downtime. We're talking about contaminated water, power outages, equipment damage, and real safety risks to real people. The Oldsmar water facility attack in 2021 is a perfect example. An attacker tried to increase sodium hydroxide to dangerous levels. That could have poisoned an entire community. Proper implementation of 62443 principles could have stopped that attack cold. Now, understanding the structure of 62443 is crucial for implementation. This pyramid shows us how all the pieces fit together, from fundamental concepts at the bottom to evaluation methods at the top. Let's start at the foundation with the 1X series general concepts. This gives us our common language, and believe me, that's more important than it sounds. Before 62443, I'd sit in meetings where IT folks talked about firewalls, and operations people talked about zones, but we weren't talking about the same things. The terminology standard, 6244311, changed that. Here's a real example from my experience. A manufacturing plant used the 1.1 terminology to create common ground between IT and OT teams. Before this, IT would run vulnerability scans that actually disrupted control equipment because of these terminology misunderstandings. Moving up to the 2X series, Asset Owner Requirements. This is the What You Need to Do section, and notice that 2.1 got a major update in 2024. Asset owners face unique challenges. You have to maintain both cybersecurity and operational reliability, often with systems that were designed decades ago when security wasn't even a consideration. I worked with a chemical plant that designated a control engineer as their OT security coordinator. Previously, security was IT's problem until something went wrong, then it became engineering's problem. Sound familiar? The 2.1 guidance helped them create clear responsibilities and coordination between departments. The 3X series covers system requirements. This is where we get into the nuts and bolts of designing secure systems using zones and conduits. How you design your system architecture fundamentally determines how defendable it is. Poor design choices can make security nearly impossible, while good designs provide defense in depth at a reasonable cost. I helped a power facility that had everything on one flat network. When they caught ransomware on a laptop, they realized their entire operation could have been compromised. Using 3.2 guidance, we divided their plant into security zones with higher security levels for critical safety systems. The 4X series is about component requirements. What security features should be built into the products you actually buy and install? Industrial components often stay in service for decades, so embedded security is essential. These standards create market pressure for vendors to build security in from the start. I remember helping a water utility that had selected systems based only on features and price. After installation, we discovered hard-coded passwords they couldn't change and unencrypted communications. Using 4.2 as a purchasing checklist would have eliminated those problems before they bought anything. Finally, the 6X series, evaluation methods. The big news here is 6244361, brand new in 2024. Most industrial organizations rely heavily on outside service providers who often have privileged access to critical systems. This standard gives us a way to evaluate those providers systematically instead of just trusting marketing claims. The 2024 updates represent a fundamental shift in how we approach industrial cybersecurity. Look at this before and after comparison. These changes make the standard much more practical for real-world implementation. The biggest change is moving from a pass-fail approach to a maturity model. The old approach basically said, you're either secure or you're not, which discouraged many organizations from even starting. The new maturity model recognizes that security is a journey, not a destination. You start at level 1, initial, where you might have some basic controls, but they're not formalized. Then you progress through defined, managed, and finally optimized levels. I worked with a manufacturing plant that felt like failures because they weren't meeting all the requirements. The maturity model showed them they actually had strong access controls, level 3, but weak monitoring, level 1. This gave them a clear improvement path instead of overwhelming them. The other major change is realistic treatment of legacy systems. You might have RTUs or PLCs that are 15 years old and will run for another 15 years. The 2024 guidance provides a pathway for securing these through compensating controls. I helped a utility with old RTUs that couldn't support encryption. Instead of a $4 million replacement project, we implemented compensating controls for under $200,000 using data diodes, enhanced monitoring, and physical security improvements. Let's talk about what this actually means for your facility. The standard gives us these 5 key areas of improvement, and I want to share some real implementation strategies. The Enhanced Security Program Framework isn't about adding bureaucracy. It's about creating clear procedures that actually work in industrial environments. Look at this example. A small water utility implemented security zones for under $5,000. The month after installation, they blocked over 30 unauthorized access attempts that previously would have reached control systems. That's a dramatic security improvement for the cost of their annual office supply budget. This chart shows something crucial: where to focus your limited security budget for maximum impact. Network segmentation and access controls give you the biggest risk reduction for the lowest implementation cost. This is where you start, not with expensive encryption projects or elaborate monitoring systems. A manufacturing plant discovered that implementing network segmentation and basic access controls at a cost of around $180,000 would address over 70% of their identified risk. This let them achieve significant security improvements while deferring more expensive measures to future budget cycles. Here's something crucial that many people miss. Cybersecurity isn't separate from safety and reliability. In industrial environments, these 3 elements are interconnected. Cybersecurity becomes an element of overall process safety. Maintenance procedures need cybersecurity considerations, and everything must align with operational reliability goals. I worked with an oil refinery that integrated cybersecurity into their process hazard analysis and management of change procedures. When designing a new distillation unit, this approach identified cyber vulnerabilities that could have affected safety interlocks, vulnerabilities that would have been completely missed under their previous approach. Let me share a story that really drives this home for me. I was called to troubleshoot a wastewater plant that lost control of several pumps. After hours of investigation, we discovered a technician's infected laptop had spread malware to the control network. The plant had spent thousands on external firewalls but overlooked internal threats. What struck me wasn't the sophistication of the attack. It was just a common worm, but how unprepared we were for even basic cyber threats. This plant had invested in redundant power supplies, backup pumps, and elaborate alarm systems for mechanical failures, yet had completely overlooked the cyber dimension of operational risk. So, where do you start? The standard gives us this clear roadmap, and I want to walk through each step with you. First, inventory your systems. You can't protect what you don't know exists. I've found undocumented PLCs, forgotten modems, and unauthorized wireless access points more times than I can count. Second, identify your critical assets. With limited resources, you need to focus protection on the systems that matter most. Not all industrial systems have equal impact if compromised. Network segmentation is your most effective control. Access controls eliminate the low-hanging fruit that many attacks exploit. And an incident response plan means you're prepared when, not if, something happens. Look at this example. A power plant operator followed emergency cards to isolate an affected system, preventing a major outage. Their response time was under 5 minutes instead of 45 minutes without a plan. Here's something that separates successful implementations from failed ones. Integrating security throughout the entire system lifecycle. Security can't be bolted on at the end of a project. It must be considered during design and procurement, implemented during commissioning, maintained during operation, and properly handled during decommissioning. A pharmaceutical manufacturer integrated security requirements into their capital projects process. For a new manufacturing line, security requirements were included in vendor specifications and validated during factory acceptance testing, saving an estimated $340,000 in retrofit costs. Here's what I want you to remember from today. Perfect security doesn't exist, but systematic improvement absolutely does. ESA, IEC 62443, provides a practical roadmap for that improvement. And you can start where you are, use what you have, and do what you can. Industrial control systems are the invisible backbone of modern society. Their security affects everyone, from water quality to energy availability to everyday products. The standards provide a framework for protecting these systems, benefiting not just the organizations that implement them, but society as a whole. Remember, the best cybersecurity implementations I've seen weren't the most expensive. They were the most thoughtful. Industrial cybersecurity isn't just about protecting data or preventing downtime. It's about ensuring the safe, reliable operation of the systems we all depend on. If this deep dive into IEC 62443 was helpful, give it a thumbs up and subscribe for more practical control insights. Drop a comment with your biggest cybersecurity challenge. I read everyone and often turn your questions into future videos. Until next time, stay safe and keep those systems secure.